Now, next speaker is Patrizio Frosini from University of Bologna, and the title of his talk is on the role of group equivariant non-expansive operators in topological data analysis. Patrizio, please go on.
So thank you so much for your invitation. This is the outline of my talk. Okay, let's start from this statement. Data analysis is not just about data. Everyone knows that when we have data, we need observers. And in many situations, we can recognize that different point of views, different observers can have completely different judgments about reality. This is quite obvious, we know that. And we can say that we are not usually interested in data, at least not directly. I do not know anyone that is directly interested in data. We are mostly interested in data observers. For example, a patient is usually interested not in the data representing a computerized axial tomography of her body, but in the diagnosis that her doctor can make from this data. And we can have plenty of examples like that. Data analysis strongly depends on the chosen observer. If data analysis were not dependent on the chosen observer, then physicians' diagnosis would always be identical, scientists would always see the same causes for each phenomenon, and all people would agree in judging who the heroes and villains in a movie or a political event are. We know that. It's something that we all know. It is indeed well known that different agents can have different reactions in the presence of the same data. And so this fact suggests that maybe we should move from the study of just data to the study of the pairs data observer. This is the set of statements or opinions I would like to move from. But in order to start with the mathematical formalization of this, the framework that is produced by these assumptions, we have to start from this question: what are data? Data are usually produced by measurements or actions made by observers. And so we need the definition of measurement. A good idea could be the one of reading Wikipedia, and we can read measurements is the assignment of a number to a characteristic of an object or event, which can be compared with other objects or events. So according to this definition, measurements and dense data can be often seen as functions associating real numbers to points of a generic set X, the set of characteristics we wish to measure. Obviously, we can speak also of vector-valued functions, but in my talk today, I'm not going to focus on vector-valued functions. I will speak just of real scalar vector functions. Some examples data, we can consider an electrocardiogram. It is a function from the real number to the real number. Obviously, not every function from the real number to the real number is an electrocardiogram, but an electrocardiogram is a function of this kind. A gray level image is a function from the real plane to the real number, or if you prefer, to an interval, for example, 0, 1. And the computerized tomography scan is a function from an helix going around a body to the real numbers. These are examples of measurements. Observers often think that some data are equivalent to each other according to some invariance group. For example, most of the people think that these two shells are equivalent to each other, since we can move a shell of a table and it maintains its own shape. So in this case, the invariance group could be the group of isometries. But if we are interested in letters, we have to recognize that we cannot say that an M letter is equal to a W letter. So in this case, the group changes, maybe the group of translations, or we can add deletions. But the group is not established once and forever. The group changes with the observer. What does it mean, equivalence between data? Imagine we have two data in this setting, two functions from a set X to R. And we say that they are equivalent if after choosing a group G of permutations of the domain X, we can find a permutation G such that phi1 is equal to phi2 composed with this permutation of our set. Instead, two functions are judged similar if we can find a permutation of a set X G such that the L infinity norm of phi1 minus phi2 composed G is small. This is a possibility, okay? And I am following this possibility of defining the concept of equivalence and similarity. These observations lead us to define the concept of natural pseudo-distance with respect to the group G. Let X be a set, a topological space in this case, and let us choose a subgroup G of a group of all homeomorphisms of our topological space X. We can now consider the infimum, this value. We can take two continuous and bounded functions phi1 and phi2 and consider the infimum varying the element in the group of the L infinity norm of the function phi1 minus phi2 composed G. This value is called the natural pseudo distance between the two data phi1 and phi2 with respect to the action of the invariance group G. I recall that the pseudo distance is just a distance without the property that d x1, x2 equal to 0 implies x1 equal to x2. And we could look at dg as the ground truth in data comparison when data equivalence is expressed by the group G. What happens when we take a trivial group as an invariance group, the identical group? In this case, the natural pseudo distance is just the L infinity distance. When we enlarge more and more the group, we tend towards the natural pseudo distance associated to the largest group, that is the group of every possible homomorphisms of a set X. In general, we restrict this pseudo metric to a particular set of bounded functions phi. Okay, so before starting with formal mathematics and theorems, I would like to list my assumptions in this approach. First of all, the space of observers is often more important, I should say much more important than the space of data. The study of a space of observers requires the development of a new topological geometric model. This new model could be of great use in data analysis when the role of observers is not negligible. These assumptions suggest us to move from topological data analysis to the new field of topological observer analysis. Observers are structures able to change data into other data, in our setting functions into other functions, and usually do that by respecting some data equivalences, for example, by commuting with some transformation in a group. As a first approximation, observers can be represented as group equivariant operators. There is a lot of people in the world nowadays working on group equivariant operators, especially in deep learning. And I could speak about Stefan Mallat, Max Welling, Tommaso Poccio, many researchers working on group equivariant operators. But in this talk, I will focus on group equivariant non-expansive operators. Why non-expansive? Because observers are often assumed to simplify the metric structure of data in order to produce meaningful interpretations. There are also different other motivations to focus on this particular kind of operators. But anyway, I will speak about this kind of operators. And I will also illustrate some interesting links between GENEOs and topological data analysis. Okay, some definitions. Let's start from a non-empty set X, not a topological space, not a topological space, a non-empty set. And let us consider a set of functions bounded functions from X to R endowed with a topology induced by the L infinity metric. Okay, we can see that X as the space where we can make our measurements, and phi as the space for possible measurements. We'll say that phi is the set of admissible functions or admissible signals. I spoke about functions that cannot be recognized as electrocardiograms, even if they are functions from R to R. So we have admissible functions. In other words, phi is the set of all functions from X to R that can be produced by our measuring instruments. For example, a gray level image can be represented as a function from the real plane to the interval 0, 1. In this case, X is a plane. I recall what is the initial topology. The initial topology, tau I, is on the set X with respect to the set phi of admissible functions, is the coarsest topology on X, such that every function phi in capital Phi is continuous. Okay, let us take on X a pseudometric. We take this pseudometric. The pseudo distance between 2 points, x1 and x2, is the supremum varying the signal of the distance, the Euclidean distance between phi of x1 and phi of x2. And this pseudometric induces a topology tau dx on the set X. So now X is a topological space, a pseudometric space and a topological space. The topology tau dx is finer than the initial topology on X with respect to phi. And if phi is totally bounded, in particular if phi is compact, then tau dx coincides with the initial topology. If we take, under the assumption that phi is totally bounded, if we take this pseudometric, we have automatically that every function in capital Phi is continuous. The use of dx implies that we can distinguish 2 points only if a measurement exists, taking those points to different values. If we have no measurements able to distinguish the points, we have to say that the distance between the points is 0. Theorem, if phi is compact and X is complete, then X is compact. So completeness implies compactness in this case. And we can, in case X is not complete, we can complete it. So we can assume that in any case, our set X is compact. And okay. Now we have another consequence, important consequence of this framework, topological framework. Each bijection is an isometry. Since let us consider the set of bijections, permutation of X, and the subset of a permutation by ij phi of X that preserve phi in this sense. If we compose a function in this set with a permutation in by ij phi of X, we obtain another function that is legitimate. It is still a signal, an acceptable signal. And the same happens when we compose phi with the inverse of G. And we can give a similar definition for the set of homeomorphisms of X, obtaining homeo phi of X, and the set of isometries of X, obtaining iso phi of X. And the proposition says that if we choose that topology on X, we have that bijections, phi preserving bijections coincide with phi preserving homeomorphism, and this coincides with phi preserving isomorphisms, isometries. Let us now focus our attention on a subgroup G of homeo phi of X. We can define on the group, our invariance group, the group we have chosen for invariance, this pseudometric. The distance between 2 elements in the group is the supremum varying the signal of a L infinity distance between the 2 signals phi composed G1 and phi composed G2. And we obtain that G is a topological group with respect to this pseudometric, and the action of G on the set of legitimate signals by right composition is continuous. Furthermore, if phi is compact and G is complete, and we can always get this result, then it is also compact with respect to the group is also compact with respect to our pseudometric. Now I can introduce formally the concept of GEO and GENEO. Each pair phi G, where G is a subgroup of a set of phi preserving homeomorphism of X, is called a perception pair. Let us assume that we have two perception pairs phi G and psi H, and let us fix a group homomorphism T from G, the group G, to the group H. Each function f from phi to psi verifying this equality, that is equivariance, is called the group equivariant operator associated with the homomorphism T. If we add non-expansivity, so we add this inequality, then F is called a group equivariant non-expansive operator, a GENEO, associated with the homomorphism T. Now, an example in order to explain what a GENEO is in practice. Let us assume that we are interested in the comparison of the distributions of temperature on a sphere. Think of the Earth, taken at two different times. We cannot recognize the countries. We can recognize just the North Pole and the South Pole, okay? The points N and S. Now, we can consider the set X equal to the sphere S2, the set of phi of one Lipschitz functions from S2 to a fixed interval AB, where A is the minimum temperature we can measure on the Earth, and B is the maximum temperature. And G is the group of rotations of S2 around the axis North Pole, South Pole. And the pair phi G is a perception pair. We can also consider the equator of our sphere, represented as a space S1, the equator of the sphere, and we call it Y. And then we can consider the set of von Lipschitz functions from S1 to the interval AB. And we can take H equal to the group of rotations of equator. Now, there is a simple example of GENEO we can give from the perception pair phi G to the perception pair psi H. As a homomorphism, we can take the obvious homomorphism defined this way. If you take the rotation of the Earth of alpha degree, this is taken to the rotation of the equator of alpha degrees, the corresponding rotation of the equator. And this is the homomorphism T, in this case, just an isomorphism. And f of phi, in this example, f of phi is defined this way. It's a function psi from the equator to the real numbers that takes each point y belonging to the equator S1 to the average of the temperatures along the meridian containing y for every distribution of temperatures. We can easily check that phi verifies the properties of equivariance and non-expansivity, so it is a GENEO with respect to our isomorphism T. There are some relevant links between GENEOs and TDA, and this is the reason I'm talking about GENEOs now at this work group. In the following, I will use this symbol, GENEO of phi G psi H, to denote the set of all GENEOs from phi G to psi H with respect to a fixed homomorphism. The first link that we can recognize between GENEOs and topological data analysis is the following one. Let us consider two functions, phi 1 and phi 2, belonging to a set of visible functions. And let us consider a subset of a set of every possible GENEO. This is F. I choose it. Now we can consider the supremum varying the operator in F of a usual matching distance, not between the persistence diagram of phi 1 and phi 2, but between the persistence diagrams of F of phi 1 and F of phi 2, the supremum varying F. So we obtain a matching distance, indeed a pseudo distance, that is strongly invariant with respect to the group. That means that these equalities hold. And the important thing is that differently from what happened for the usual bottleneck distance between the persistence diagrams, this distance is not invariant with respect to every homeomorphism of a space X. And this is important. I have shown the example of the M letter and the W letter. We don't wish that the two objects are considered equal to each other. So it is important to have a distance in topological data analysis that says they are different. And this distance depends on GENEOs. Okay, another statement. Let us assume that phi is the set of all Morse functions from a closed regular manifold M to the interval 0, 1. We take these functions and we take the group of all self. I'm wrong here. We should consider not self-homomorphism, but diffeomorphisms. Phi is the set of all linear combinations of functions, linear combination of this kind, where pi is a finite subset of extended plane, so we accept also points at infinity, and f is a 10th function, so functions like this. Okay, the usual 10th function. And we have inside the linear combination value infinity norm. So we replace, okay, this is the set of functions, this set of admissible signals. H is a trivial group containing only the identity from R2 to R2, and the homomorphism T is the trivial homomorphism between G and the trivial group. The only homomorphism we can have. Then the operator taking each function phi, each signal, to the linear combination associated with its persistence diagram is a geneo from phi g to psi h with respect to t. So what happens? I take a function and I take the persistence diagram and I replace each point in the persistence diagrams with a 10th function in 2 dimensions. Okay, so I have an operator transforming functions into functions. This is a geneo. And this follows from the equivariance of from invariance of persistence diagrams under the action of self-homomorphisms, and in particular under the action of self-diffeomorphisms, and non-expansivity is a consequence of the stability of persistence diagram. So in some sense, persistence diagrams can be seen as GENEOs, in some sense. Computing DG via GENEOs and persistent homology. This is an important point. It is not easy to compute the natural pseudo distance, but if we take the set of every possible GENEO and we consider the distance I have introduced previously, we can prove that the distance associated to the set of every possible GENEOs coincides, for the group G, coincides with the natural pseudo distance associated with the group G. So it is important to observe that there is a link between the natural pseudo distance and GENEOs. So GENEOs allows us to approximate the natural pseudo distance, DG. GENEOs and 2-parameter persistent homology. Imagine that we have a bifiltration given by a function phi from topological space X to R2 with components phi 1, phi 2, and let us consider a unit vector with respect to the L1 norm, that is W equal to A1 minus A with A belonging to the interval 0, 1 with a positive slope. Okay, so A belongs to the interval I told you. And the point B minus B. Every choice of a point and of a unit vector W defines a filtration, we well know this, xt of x, where xt is the set of points of x whose image by phi is both under and on the left of a point P plus TW. As a consequence, each choice of P and W defines a persistence diagram. So we take every possible positive slope line, the yellow line here, defined by the point of the unit vector, and we go through this line and we take the points that are both under and on the left of a point. So we get a filtration of a space. In this case, the space is a curve in R2 as the filtering function is the identity. What happens? It happens that we can write the point xy as p plus tw, that is this in this way, and we can consider the function phi ab, depending on the parameter a and b, that is depending on the line, defined this way. And the important observation is that the sublevel set can be expressed as the set of points P such that phi AB is less than or equal to. And we know that in theory, in order to have stability, we have to normalize this function. We have to multiply this function by the minimum between A and 1 minus A. If we do that, we obtain a new function phi star AB that allows us to prove a stability theorem. We define this distance between functions. We take two R2 valued function phi and psi. We define the distance as the supremum varying the line, that is varying the pair AB, of a matching distance between the persistence diagrams of phi star AB and the persistence diagram of psi star AB. And the stability theorem says that this distance is less than or equal to the infinity distance between phi and psi. And this result, it is well known, that can be easily extended to n parameter persistent homology. Why did I tell this? I told this because, in summary, the definition of a matching distance in two-parameter persistent homology depends on this operator. FAB, taking h function phi to phi star of AB with AB, that is this maximum. The interesting statement is that this operator is a geneo. So when you decide to introduce two-parameter or n-parameter ranking variant, it's important to recognize that it can be introduced. It can be introduced by presenting the GENEOs FAB varying the pair AB. Finally, since until now we have just given 4 different examples showing the use of GENEOs in order to study topological data analysis. But now I would like to give an example of the use of topological data analysis in order to facilitate, to make easier the study of GENEOs. And it is based on this pseudo distance. We can consider this pseudo distance between GENEOs that is defined this way. We take the supremum varying the legitimate signal, the admissible signal in the space capital phi, of a matching distance between the persistence diagrams of F1 of phi and the persistence diagram of F2 of phi. And this is a distance that is quite of use in order to compare GENEOs. We can also have a distance of this kind for the group, but I skip this point due to the limit of time. 2 key results are the following one. If we take this pseudo distance, the usual pseudo distance between operators, but what I'm saying it also holds for the distance that I've introduced previously in the previous slides. If we take this metric between operator, we have these 2 theorems. First of all, if phi and psi are compact, then the set of GENEOs is compact with respect to this distance. In some sense, I could say if the spaces of data are compact, then the space of observers is compact. And this strongly depends on the topology I have introduced. Without that, this statement is false. If the space of data is convex, we have that the space of GENEOs is convex too. So This is important for application. I skip this result. It is just a result saying that we can approximate. We can indeed approximate this pseudometric in practical cases. Methods to build GENEOs. It is interesting to observe that there are some elementary methods to build GENEOs. The composition of two GENEOs is still a GENEO. The image by a one Lipschitz function of a set F1, Fn of GENEOs is still a GENEO with respect to the same group. Then, if we take the maximum of a set of GENEOs, this is still a GENEO. If we translate a GENEO, this is still a GENEO. If we take, this is trivial since I told you that the set of GENEOs is convex, the convex combination of GENEOs is still a GENEOs. So we have a machinery to build new GENEOs starting from previously existing GENEOs. But I would like to show you something more interesting from a mathematical point of view about building GENEOs, the concept of permutant measures. Let us consider the set capital phi of every possible function from a finite set capital X to the real numbers. And let us consider a subgroup of a group of every possible bijections of a finite set X. So this is a set of every possible permutation. Definition, a finite sign measure mu on the set of permutation is called a permutant measure with respect to our invariance group if every subset H of a set of permutation, of a group of permutation, is measurable and the measure mu is invariant under the conjugacy action of a group. So this equality holds. In this case, if we have a permutant measure, we can build a GENEO. For each permutant measure, there is a GENEO. If mu is a permutant measure with respect to G, then the map taking each function, I do not know if you can read this. The function taking each function phi to the sum over the set of every possible permutation on X of a function phi composed with H minus 1 times the measure of the permutation H, this is a linear GEO. It is a GENEO if the total mass of a measure is less than 1. An example of a permutant measure. Let us consider the set X of the vertices of a cube in R3 and the group G of orientation-preserving isometries of R3 that take X to X. Let pi1, pi2, pi3 be the free planes that contain the center of mass of X and are parallel to a face of a cube. You can see the free planes in the picture. Let HI be the orthogonal symmetry with respect to pi I. We can now define a permutant measure mu on the group of the permutation of X by setting mu of H1 equal to mu of H2 equal to mu of H3 equal to a positive real number C, and mu of H equal to 0 for any other permutation. This is a permutant measure. Please note that the cardinality of the support of a permutant measure is free, but is much less than the cardinality of a group G, if that is equal, if I'm not wrong, to 24. So the sum involving in this process involves just three elements. Theorem. I have this presentation theorem. Let us assume that G is a group of permutations that transitively acts on the finite set X, and that F is a map from the space of functions Rx to Rx. The map F is a linear GENEO with respect to the identical homomorphisms if and only if there is a permutant measure mu with respect to the group such that f of phi is equal to this sum. And the total mass of a measure is less than 1. So we can obtain GENEOs by permutant measures. I'm going to finish my talk by saying something about the probabilistic setting. I'm going to skip many theoretical details here. just a general view. When the space of data W is endowed with a probability measure, we can replace the pseudomatrix dx dg that we have defined previously on the set X and on the group G with following two pseudomatrics delta X and delta G, after choosing a G invariant probability density F and a G invariant probability measure lambda on the set of admissible functions. In practice, we consider the expected value of the distance between the images under the action of the functions. In the following slides, I'm going to assume that the set of admissible function, capital phi, is compact. Okay, the good news is that the properties that we have seen in the deterministic setting still hold in the probabilistic setting, since we can prove that every function in the admissible set of functions is continuous with respect to our pseudometric. The set X is totally bounded with respect to our pseudometric, and if X is complete, then X is compact. The same also for the group. We can say that G is a topological group with respect to our topology associated with our pseudometric, and the action of G on the set capital phi by right composition is continuous. G is totally bounded, and if G is complete, then it is also compact. Theorem, we have that also in the probabilistic setting, after adapting the definition of GEO and GENEO, we can prove that if the space of data, the spaces of data are compact, then the space of all GENEOs is compact with respect to this norm. And if the spaces of data are convex, then also the set of all GENEOs is convex. An important remark, if we consider the Bochner space L2 phi V of the maps between the set of admissible signal phi into another space of admissible signal, a vector space in this case, this Bochner space is endowed with the inner product, this inner product here. Therefore, any CK submanifold GENEOs in the Bochner space naturally inherits a Riemannian structure. And this means that we can imagine of building manifolds of observers, manifolds of GENEOs, and we can move along these manifolds by following a gradient flow in order to optimize our GENEOs in the manifold. Okay, in case you are interested, you can find information in the PDF that I will make available. Conclusions, there are many links between topological data analysis and theory of GENEOs. The theory of GENEOs could be a starting point for moving from topological data analysis to topological observer analysis. The computation of suitable representation of persistent diagrams can be seen as a GENEO. The use of GENEOs allows us to restrict the invariance of TDA to suitable to the group we can choose. GENEOs and persistent homology allows us to approximate the natural absolute distance DG. GENEOs interact with multi-parameter persistent homology. And finally, GENEOs can be efficiently compared by means of tools in topological data analysis. In perspective, what we would like to do is to obtain a good compositional theory for building efficient and transparent networks of GENEOs. And some preliminary experiments suggest that replacing neurons with GENEOs could make deep learning more transparent and interpretable and speed up the learning process. Open questions. There are several questions. How can we approximate the real observers by GENEOs in order to emulate their behavior with respect to data? Can we devise constructive procedures allowing us to build any possible GENEO with respect to a given equivariance group? What is the right way of comparing GENEOs in a topological statistical setting? How should we select representative sets in a probability space of GENEOs? How can we compute the basic statistics for GENEOs? How can we predict the behavior networks of GENEOs and control their actions? How can we evaluate the advantages and limits of an approach data analysis based on the interaction of GENEOs and TDA? Okay, these results have been obtained by collaborating with many collaborators. I write their names here in this list. And if you are interested, you can have a look at these papers, in particular to this look towards the topological geometrical theory of group equivariant or expansive operators that presents most of the topological setting that I have introduced. And that's it. Thank you for your attention.
Thanks a lot, Patrizio, for a very interesting talk. So it's now again time for questions or comments. So again, please put cues on the chat list. Meanwhile, I have a small question, Patrizio. Since in the general theory you consider you allow any in some theorems any subgroup of the group of bijections, in practice, what do you expect or what you know already from experience? How does this affect a practical application? Because this group could be quite huge.
The group of permutation is the group of isometries. And please remember that we are not going to accept any possible permutation. We are just accepting permutation, preserving the space of admissible signals. So you cannot take an image and mess up the points. Since in this case, you go from an admissible signal to a signal that is not accepted. So we are not considering any possible permutation.
I see.
Everything is based on the admissible signals.
Okay. Thank you. So there is a question from Wojtek.
Thank you, Patrizio. Great talk. So Patrizio, I have a question. So, even if we choose a small number of, let's say, of a small group, still when we make some measurements, these groups, we might make some errors, right? So it's sort of hard to, for these, group actions to preserve such data, right? So somehow the GENEOs somehow are, there's lots of you have to have there's this rigidity.
Yes, you have to consider that the main point is focusing on the concept of observer. An observer can compress data, okay? And so in case you have noise, it's due to the observer to choose a method that make this noise under control. For example, in our last paper, we consider a particular case of operator that is suitable in order to eliminate some kind of impulsive noise from data, and it is a GENEO. So the general idea is this one: you have a problem for example, in deep learning. Choose a set of observers that are quite you think that are quite important in that matter, in that problem, and then try to combine by precise mathematical rules these operators. Obviously, if you are interested in noise, and anyone is interested in noise, you have to insert in the set of GENEOs that are charged of the duty of controlling noise. For example, that kind of operators, I have no time to speak about that now, but there are operators that are thought as controllers of noise. This kind of thing.
Okay. No, I mean, I guess you are aware of it. The one I'm interested in, to encode the symmetry, is that you start with some measurements, some observables, and then you add these symmetries by sort of precomposing with various group actions, and then somehow get more observations. I mean, it's just a great talk. Thank you.
Thank you.
So Kevin, a question from Kevin.
Yeah, I have a quick question. This is a very interesting talk. So I just want to try to understand what is the computational cost, or how is it easy to implement this model, say for like protein or DNA, this kind of like a complicated 3D structures.
Okay, essentially we have just 2 experiments we have made about this. One in the paper written with Mattia Bergomi, Nicola Quercioli, and the paper I have shown. Maybe I can this one, the last one. And here we consider a projection of the data that allowed us to speed up the process, the learning process, but I cannot quantify. In the paper, this is not my part of the paper. Maybe Mattia could answer about this, but we observe that there is a strong reduction in the learning time. There is another application in pocket detection that I'm doing with in proteins, that I'm doing with some colleagues in the University of Milan, Pedretti, Bocchi, and Micheletti, that shows that we can, instead of using huge, not huge maybe, but large neural networks with hundreds of millions of neurons, we can restrict to just, let me say, thousands of parameters. Since the idea is like that, instead of looking for every possibility, just look for interesting, the combination of interesting observations. So this is the huge reduction. Since this is quite interesting, during COVID, I had the time of reading an interesting paper in Evo Evolutionary Development, written by Sean Carroll, Endless Forms, Most Beautiful, that says that in nature produced in biology, nature produced just a few modules. The same module for arms, for legs, for wings, the same module. So the idea is that we should think of having just a relatively small set of modules, in this case, GENEOs, and we should try to combine them, maintaining invariances. This is the idea in order to build this mathematical structure of topological observer analysis instead of a topological data analysis.
Yeah, thank you. Yeah, very interesting.
Any more questions? I do not see any more questions on the chat. So let's thank Patrizio again. And this completes the first today's session.